So, welcome to module 6 and we are looking at process scheduling. Now, what do you mean by scheduling? So, I am scheduling my classes tomorrow, I am scheduling a meeting tomorrow. That means what we say, that you assign, somebody wants a resource and you assign a timing at which you assign that particular element to that resource, right. I schedule a class means students want to learn hopefully. Now, so I say at 9 o'clock there is a class, so I schedule that class means that students need to come at 9 o'clock to attend to that class. So, I am assigning the student to a classroom which is a resource at a particular time, right. So, this is what we mean by scheduling, right. It is a very simple example of scheduling. Now, let us look at what do you mean by process scheduling. Process scheduling here is that I want to assign a process to the CPU at some time. That is why we call it as process scheduling. Scheduling what? Scheduling process to whom? To the CPU, right. So, I want to schedule a process to a CPU at a given time. So, this is why we call it as process scheduling. Okay. Now, we can also call it as CPU scheduling. Now, what is the challenge here? Now, there are, so already I told that there are several fellows waiting, several processes waiting. This can be applicable to threads also. There are several processes, we will just say it is now processes which covers also threads. There are lot of processes waiting in a ready queue. There is only one CPU. Now, the operating system should go and pick one process from these people waiting there, these processes waiting there, and assign it to the CPU, get it executed, then it has to get another, right, and this is the challenge. Now, what is the challenge here? I want to see that all the processes get executed, nobody should feel that they are waiting, right. You are going to a server, let us say you are going to a mail server, the scheduler in the mail server should see the moment you click your mail should come. If you take half an hour for that mail to come, you get really frustrated, right. This is a user level experience. So, it is better to understand the role of a scheduler. The scheduler, there are millions of users trying to access say their own mails. Let us take the example of a mail server. There are millions of users who want to actually go and read their mails. Everybody wants to look at it faster. Now, that means every time somebody logs in, a process is created. So, there are millions of processes waiting on the scheduler queue, and I do not have millions of CPUs, I have limited number of CPUs. Now, there is a scheduling algorithm which will take one fellow, each process assign it to a CPU and then remove it back, etc., and it should be done in such a way that the user never feels that there is a delay, and that is the challenge, right. So, that is the entire aspect of scheduling. Now, the scheduling part of the operating system has two components, one is called the scheduler, another is called the dispatcher. The scheduler looks at the queue and finds out which process I need to schedule. Once it identifies that process, the dispatcher will take that process and put it into the CPU, right. So, these two are two important components of a scheduler. Now, why does scheduling work? Now, when we execute a program is a collection of CPU and IO. You even take the simple hello world, right, there is a printf hello world. So, you assign something to a string, say hello world to a string and print that string. So, there is some computation involved where you actually assign that hello world to a string, and then immediately there is an IO whether it is going to write on your console the hello world. So, even the simplest of the simplest program that you have written has a small bit of computation and a small bit of IO. So, if you look at programs in general, this is an empirical study. I can write a program which does not do any IO at all, mainly it may not make any sense, but the majority or 99.999% of the programs do have lot of CPU activities and lot of IO activities. Now, IO is real IO in the sense that it takes lot more time than the CPU, right. It is much slower than the CPU. So, if I do say 10 IO operations, at that time I could do thousands of CPU operations. That is the difference. So, the I/O is much slower than the CPU. So, now let us talk about the mail server again. I have hundreds of processes. Now, each process will have its CPU activity followed by an I/O activity, again a CPU activity followed by an I/O activity, etc. So, this alternating sequence of CPU activity, I/O activity, CPU activity, I/O activity, this is how a program executes, and each CPU activity is called a CPU burst, and then I/O burst, then CPU burst, then I/O burst. The CPU burst, the I/O burst need not be essentially equal. The I/O burst will take much more time than the CPU burst for reasons that I have basically talked. Now, when an I/O is happening, the CPU will not do anything, because the I/O is happening between the I/O device and the memory. Mostly the notion of a direct memory access, or DMA, will be used, and so the I/O will never involve the CPU. So, let us take the top diagram on your right hand side. Now, what happens is, we have only one process. That process does some CPU activity, then it does the first I/O operation. When the first I/O operation is happening on the disk, the CPU remains idle, and then while the first CPU operation was happening on the CPU, the disk was idle. So, the CPU is doing something, disk is idle, then the CPU becomes idle, then the disk starts working for the first I/O operation. When the first I/O ends, again CPU starts working till the second I/O operation, and in that period between the I/O ends and the second I/O operation, your disk is idle, and again disk starts the second I/O operation, and till it ends the CPU is idle, and now again CPU starts the operation, and till the third I/O operation your disk is idle, and when the third I/O operation starts, your CPU is idle till it ends, and so on and so forth. So, the disk and the CPU are not. So, the question is, when the CPU is idle, why can't it do the CPU activity of a second process, and that is what you see in the next diagram that is below on your right hand side. So, when the CPU does the first job, of course disk is idle, the first job asks for an I/O operation, this starts doing the I/O operation of job 1. At that time the CPU can do the job 2, the CPU burst of job 2, and then in this context I just put the I/O is much slower than the CPU, or I/O is faster than the CPU. Now, when the CPU, when the job 2 wants to do an I/O operation, it goes to the disk. At that time the job 1 can be rescheduled onto the CPU. Again, when job 2 finishes, job 2's I/O finishes, job 2 can be rescheduled onto the CPU, while job 1's I/O can be done, right. So, now you note that there is a overlap of the I/O and the computation here. So, almost at the same time two jobs can be executed almost concurrently, and every job feels that they are given some time, right, and their I/O is also happening here, right. So, this particular property, that any program that is executing is an alternating sequence of CPU burst and I/O burst, and that when an I/O burst is happening, the CPU is idle with respect to that program, and when the CPU burst is happening, the I/O is, the disk is idle, or the I/O peripherals are idle, and this property and this feature is basically exploited to start executing multiple programs at the same time. Number of processes that are executed at a single point of time, the maximum number of processes that could be executed, that is actually called the degree of multi-programming. The degree of multi-programming is equal to the maximum number of processes that are simultaneously being executed, being admitted into the system. They can be in one of these states, running state or suspended state or waiting state. Running, if I have say 4 CPUs, I could have at most 4 processes that are running. Lot of things can be in waiting state, lot of them can be in ready state. Put sigma of all these numbers, and that is what we call as degree of multi-programming. Okay. Now, there are 2 types of jobs that we see. One is as CPU bound jobs. For example, matrix multiplication is a CPU bound job. Why? Because I have n cube multiplication, while only n squared, order n cube multiplications, right, if I want to multiply 2n by n matrix, but I have only n squared I/O. I have to read 2 matrices, and size of each matrix is n squared, right, while matrix addition is an I/O bound program. because I have only n squared addition and I have n squared IO operations, and IO operations are much more costlier than compute operation. So, a simple example of what a CPU bound program and a IO bound program comes even from our first programming examples that we learn in life, like matrix multiplication versus matrix addition. So, in IO, both in the context of a CPU bound program and a IO bound program, this scheduling is valid as a concept. Now, you see job 1 is more CPU bound, while job 2 is more sort of balance between, it has more larger IO operations. So, if I have a mix of CPU and IO bound jobs, then this type of a scheduling really helps. So, what are the scheduling mechanisms? There are 3 types of scheduling. One thing is a long term scheduler, which basically is done for batch jobs, right. So, I submit some jobs tonight and tomorrow morning I go and collect the results. It is not interactive programming. That still you do in your high performance computing systems or supercomputing, where you have a large job to be executed, large finite element simulation, you go give it in the night and tomorrow morning you collect. So, these type of schedulers are called long term. Term in the sense it is anything more than 10 minutes is a long term scheduler, okay, where the program is going to be assigned to the CPU for more than 10 minutes or so, we can call it as long term scheduler. There is something called medium term scheduler, which is in between short term and long term, and a short term scheduler is something like what you see on a mobile phone. I click something, immediately something comes and then it's gone, right. So, this is more for real time share interactive operating systems. These are the short term schedulers are very, very important. Now, a long term scheduler is invoked in seconds or minutes, once in a second or minute, while a short term scheduler is invoked every millisecond or tens of milliseconds, right. So, this is the difference. So, what we will be, we will be covering scheduling algorithms which are true for both long term and short term scheduling, and we will see how this could work. So, what is the role of a CPU scheduler? To sum up, the role of the CPU scheduler is there will be somebody who is running and it should switch from running to waiting state, and or it can switch from running to ready state, and it can also switch from waiting to ready state, or it can terminate. So, a scheduler for every process it can make one of these decisions, right. It can switch a process which is currently at a running state to a waiting state because it asked for some service from the operating system. It can switch it from a running state to a ready state because it was an interrupt. The process did not ask anything, there was an external interrupt, so I can move it from a running state to a ready state. I can also switch it from a waiting state to a ready state because some system call is completed. A process actually asked for a system call when it was running, so I put it on to a waiting state. Now that system call is finished, so I can move it on to a ready state, or the process has actually terminated or it has done some divide by 0, some exception thing which it cannot continue. The scheduler can go and terminate a process. Now, there are 2 types of scheduling, non-preemptive and preemptive. These are all operating system topics, but we tend to learn those things now because these are security implications at a later stage. What is non-preemptive? I cannot stop the process when it is executing through an external interrupt, right. So, I cannot pull out the process when it is executing. So, that is what we call as non-preemptive, unless the process itself comes out. So, if I start executing a process, I cannot preempt it till it comes out, right. And similarly, there is something called preemptive process, in which I can pull out the process at any point of time, okay. So, there is a huge amount of security implications, especially when there is a non-preemptive process, because when it goes in and I cannot interrupt it, I really do not know what it is doing. It can do lot of things and it can hide what it has done, so that at a later point it can unhide it and take it forward. So, non-preemptive scheduling especially of tasks has security implications, and we will look at it in great detail when we go to the remaining part of this course and subsequent courses. So, now the next thing is there is a scheduling algorithm. We will talk about these algorithms in some depth in the next module, but please do understand that after the operating system decides that this is the process that needs to go to execution, then it gives that link to the dispatcher. And so, what will the dispatcher do? The OS code that takes the CPU away from the current process and hands it over to the newly scheduled process is called the dispatcher. So, this is responsible for doing the entire task switching, okay. And the dispatcher gives control of the CPU to the process selected by the short term scheduler or the long term scheduler. In this case, more it will be valid in the case of short term scheduler. So, what it means that I switch context from one process to another process, and then I also switch back to user mode, because the dispatcher, if it is a kernel level thing, the scheduling is a kernel level algorithm. So, essentially the dispatcher is also working at the kernel level. So, now I have to switch back to the user mode and start the program. So, the user program should execute at the user level. Please note, there is a very subtle point here. I switch to the user board and then give control to that program. So, I do not give control to that program and then ask it to switch to the user mode. That is a security vulnerability. So, the dispatcher role is, I have decided, operating system decides which should be the next job to be scheduled. Now, the dispatcher goes and does all the context switching, all the saving of the old process information and collecting the loading of the new information, etc. And then it will first switch to user mode and then give control to the program. This sequence is extremely important. So, these are some small subtle things that I want you all to understand, so that tomorrow when we start looking at OS level security, these points need to be extremely taken care of. So, this is very important that I first switch to user mode and then give control to the user program. If I give control to the user program and then ask it to switch to, that means the user program for some point will be running in the kernel mode. Essentially it has more privileges and it can create issues. Now, there is of course a latency that is created, and that is very important, that distinguishes us between scheduling between threads versus scheduling between processes. This is dispatch latency, is the time it takes for the dispatcher to stop one process and start executing another. Now, we have already talked about preemptive and non-preemptive. As a process, I relinquish CPU because I did a mistake. It is called a trap. I did a segmentation overflow. I accessed a page that does not exist. I accessed a segment which is, I went and start writing into a segment which is read only. I start writing into a code segment. I start executing from a data segment. My stack has overflown. Right? I access a page that is not there. Right? All I divide by 0. So, these are all called traps, and I come out, because once a trap comes, immediately the hardware will detect that there is a trap, and it will basically go to an interrupt service routine. Interrupt service routine, the context switch automatically to interrupt service routine. An interrupt service routine is a part of your operating system. So, the operating system gets control, and then it will basically pull out this process saying, why did you do it, right. So, this is basically what we call as a cooperative scheduling, a part of cooperative scheduling, in the sense that when there is something wrong, the process cooperates with you and it comes out. It can also be that the process themselves, if they think they have done so much of CPU, it want to give others a chance, it can come out. So, this is cooperative scheduling, where the OS does not have a control of stopping a process that is executing. This cooperative scheduling is also called as non-preemptive. But a preemptive scheduling is something where the OS goes and stops a current process and gets it out. How will a OS go and stop the current process? It cannot stop, because OS itself is a program. It has to execute to stop somebody else, but somebody else is executing. Now, how it does is that it programs an interrupt, for example, timer interrupt. Right? Timer interrupt can get out at any point of time. So, it goes and programs that interrupt. So, when the operating system is in execution, it is executing on the CPU, it goes and programs this interrupt and then comes out. After it comes out, it cannot execute. So, it is dormant. Some other process will be executing. The hardware interrupt will go at that particular time, since it is programmed, it will click, and moment the hardware interrupt goes, the control now comes back to the interrupt service routine, which is part of the operating system. That is how a CPU, an operating system which is dormant, can get control over the CPU or get access to the CPU through what we call as hardware interrupt. So, the key word is interrupt, and this is a hardware level feature that is required for preemptive scheduling. And so, what is preemptive scheduling? As we will see in the scheduling algorithms that we are going to see in the next module, we will say that the preemptive scheduling will stop a process from running away with the CPU, meaning it will have the CPU for eternity, essentially not allowing the other process. So, a preemptive scheduling actually avoids what we call as a starvation of a process. That a process will not wait for long for getting into the CPU. So a preemptive scheduling algorithm can basically help in getting processes get access to the CPU within reasonable amount of time. Now when we talk about preemptive scheduling, it brings up new issues of its own, like coordinating access to shared data and can you interrupt and interrupt, etc. So these are all some questions that are coming up, which we will answer in the subsequent lectures. So this slide basically summarizes what I have explained so far, the difference between preemptive scheduling and non-preemptive. Note that preemptive scheduling is to remove the process forcefully and get the OS executing, and that is possible only by the hardware interrupt. So you have to program the timer, and the timer interrupt will when the operating system is executing, it has to program the timer, and when it comes out, when the process is executing, the timer will generate an interrupt based on which the current executing process is preempted. So hardware timer based interrupt is extremely necessary for doing preemptive scheduling. In non-preemptive scheduling, the running process can only lose the process voluntarily by terminating or by requesting an IO, or one CPU given to a process, it cannot be preempted until the process completes its CPU burst. So this is the difference between preemptive and non-preemptive scheduling. So as I had explained in the previous slides, that a job essentially has a CPU burst and a IO burst. So any IO bound program typically has many short CPU bursts interlaced between IO bursts, and a CPU bound program might have a few long CPU bursts. And we already saw that in the previous section, that if I have more than one processes that could be executed, the CPU burst of one can be merged with the IO burst of other and vice versa, and basically you can achieve good CPU utilization. At the same time, I can also do the IO device utilization. So I can merge the CPU burst of one program with the IO burst of another program and see those concurrency. And so since this is possible, now I need somebody who will tell who should execute when, and so there is a need for coordinating this activity, and that is the role of a scheduler. So suppose I want to design a scheduling algorithm. What will the scheduling algorithm do? So these are all the programs that are waiting. Which of the programs should be scheduled next? It has to make this decision. And while making this decision, there are some criteria that it needs to get out. One is CPU utilization. Always the CPU should be used. But that alone cannot be enough criteria, because I have a very big program and I say always that program will execute, you will have maximum CPU utilization. But the other fellows will be dying or they will be starving. This is called starvation. So other important time that I am looking at is throughput, which is the number of processes that complete their execution per unit time. The moment I look at throughput and CPU utilization together, now I have got some notion of reducing the starvation, right. So if I have one program that is executing for 100 units of time, and if I have two more programs there which is executing for 25 units of time, then if I just put that 100 units of program forever, I will get good CPU utilization, but the throughput will be just 1. But I can just do that, I can finish off 125, another 25, and then this, my throughput now will be 2.5, because within the same 100 units of time, two programs have completed of 25 each, and another program which is 100 units, 50 units of it has been allocated. So if I look at throughput and CPU utilization together, slowly I am bringing in the notion of reducing the starvation. The next thing is turnaround time, which is amount of time to execute a particular process. There is also waiting time, the amount of time a process has been waiting in the ready queue, because if it is waiting for something else in this waiting queue, if it is waiting in the waiting queue for some IO operation, it is depending upon how fast the IO device can work. So that is not a problem of the scheduler. The problem of the scheduler is it has to keep this fellow, if somebody enters the ready queue, it should be sent out as early as possible. If a process spends more time in the ready queue, then the scheduler is not so effective with respect to that process. And then the response time, amount of time it takes from when a request was submitted until the first response is produced. Please note that it is not the output, full output. I say something, that fellow say yes, I am here, and it puts some window saying processing. You got this? right, and that becomes extremely important. The response time is, I ask for service, how quickly I get a response saying I know that service exists, we can, because that gives us more confidence in a fail safe operating system. Somehow if the service could not be met, at least some fail safe action will be taken. So in a real time operating system, this response time is extremely important. So how do we calculate the waiting and turnaround time? The waiting time for a non-preemptive process is the start time minus arrival time. So the process comes in, it is staying in the ready queue, that is the arrival time, and then it starts. After it starts, it never comes back because it is a non-preemptive thing, it goes and completes. So the start time minus arrival time is the waiting time on your waiting queue. For preemptive algorithms, it is finish time minus arrival time minus CPU time, right. So after it arrives, it stays on the ready queue, and at times it goes to the CPU, again it comes back, again it goes to the CPU, and again it comes back. So finish time minus arrival time minus CPU time. So this is the total waiting time. So the turnaround time, waiting time is different from turnaround time. Turnaround time is nothing but finish time minus arrival time. So this is how we calculate this. So to sum up, I need to maximize the CPU utilization, I need to maximize the throughput, I need to minimize the turnaround time, I need to minimize the waiting time, I need to minimize the response time. These are all the criteria based on which I need to do my scheduling algorithm. And I can do many things. I can either do min max, that is how bad can the worst case scenario be, those type of things I can take care, right. So I would like to have a control over the worst case behavior. So I could design algorithms which will optimize in the sense that the worst case behavior will not be really worst. I could also design algorithms in which the average case will be excellent. The worst case can be bad, but it will happen once in a blue moon. The average, where you can go and reboot the system, etc. The average case would be very good. So I could keep designing algorithms in which I could have varieties of ways by which I could look at these criteria for optimization. But the most important thing is the second point. I need to minimize the variance in measure. I can't say one time it will be so fast, another time it will be very slow, right. I should be either slow always or I should be fast always, right. So then only people will get a confidence in your system. If it is so non-predictable, sometimes it is extremely fast, sometimes extremely slow, then variance is there, then the confidence in your operating system. You can't say it is a slow one, you can't say it is a fast one, right. So there should be some determinism in the variance, that now my process enters, the time by which it will come out, there should be some fixed binding limits, and that is what we say as minimize the variance in this measure. So I could not have these measures, one time the measure is 100, one time the measure is 0. Then I don't know what to do with this measure. So this is very, very important. So these are all the criteria for optimization, and when we start doing these optimization, when we start looking at different ways by which this criteria could be managed, each way of managing this criteria basically gives me a different scheduling algorithm. The purpose of a system determines the appropriateness of a criterion. See, that is very, very important. So as I told you, when I am looking at a program, right, I am very happy about throughput. When I am looking at a real time system, I am not bothered about throughput, I am bothered about response time. But when I am looking at a batch, right, I am more happy with the throughput. As a programmer, simple programmer writing a conference paper and tomorrow morning I need a simulation to come out, I am interested in the turnaround time. So different users who use the operating system will have different perspective of what is efficient scheduling, and that is very, very important, okay. So typically people will look at maximizing CPU utilization and throughput and minimize the response times. So this is where we stand. Okay. So with this we come to the end of this module. The takeaway from this module is that scheduling is important, and there are some scheduling algorithms. We will discuss more about the scheduling algorithms in the next module, while in this module we have talked about some basic principles of scheduling and also some theoretical framework and certain optimization criteria for scheduling. Thank you.